Okay. Yeah. Okay. Well, we're going to do math. Okay. So remember where we are. We're talking about continuity and compactness, right? So, right, chapter 2 was all this stuff about open sets, closed sets, point set topology, and primarily compactness. And now we've jumped into chapter 4, and we're talking about continuity. The first thing main thing we're talking about is continuity and compactness. And one of the big results that we got was the extreme value theorem, right? So that that showed why why we had that theorem back in calculus 1. And then the next sort of like the next unit is next subsection is continuity and connectedness. And that's going to be related to the intermediate value theorem. If you remember the intermediate value theorem, it says something like, whenever you have a point, whenever you have a value and you have another value, if your function is continuous, then whatever intermediate value you choose is going to be attained somewhere, right? So if you take an intermediate value between f of a and f of b, then you're guaranteed that it's going to be attained. You can't skip over that value. And as you see, that is basically a statement about connectedness, right? So yeah. So that's pretty much the last big thing we do in this chapter. But before we get there, we're going to talk about a really important idea, which is uniform continuity. Okay, uniform continuity. Okay, and so here's how you want to think about it, right? So so continuity, remember, so f continuous at a point. Can somebody tell me what that means? What does continuity at a point mean? So you've got a function going from one metric space to another, and you've got a point in the domain. What does continuity at a point mean? Take 10 seconds and write something down. Write down what continuity at a point means, just to make sure that you have it. Or imagine in your brain what it is. So I said at the beginning of the class that, in some sense, math is the study of these objects that we create via definitions. So, this is how we make the things in our mind, right? The definitions are how you have this definition, and then you create this sort of construct in your mind of that definition, and then those are the objects of study. So it's really, really crucial to have the definitions down. Okay, so make sure that whatever definition we have, you know what it is, because otherwise, it's like you're not looking at the object that we're studying. Right? You have to know the definitions. Somebody tell me continuity at a point. Anybody? Should I choose somebody at random? No, I don't have my random number generator. Yes, go ahead, Anne.
It's continuous at P if there's a delta neighborhood around P that gets mapped, whose image is a subset or is contained within epsilon neighborhood of f of P.
Okay.
For every epsilon.
Right, so you have to phrase it in the right way. Just now you said, and this is, you said, if there's a delta neighborhood such that the image is contained in some epsilon neighborhood. But it's actually, it's actually sort of, you have to say it the opposite way. Say, no matter what epsilon neighborhood you're given, there's a corresponding delta neighborhood. So it's this association, right? Like whatever epsilon neighborhood you're given, there's a delta neighborhood that gets mapped into it. Okay, if I say there's a delta neighborhood that gets mapped into some epsilon neighborhood, then even something like this would work. Even something like this would work, because you would say, well, look, here's a delta neighborhood. Here's a delta neighborhood, and it gets mapped into, so here's f of p. It gets mapped into this epsilon neighborhood, right? I found an epsilon neighborhood that works for this delta neighborhood. Okay, that's the opposite. Rather, you want to find delta neighborhoods that work for the epsilon neighborhoods, right? So it has to be said in the opposite way. Yeah. So no matter what epsilon neighborhood of f of p is given, there is a corresponding delta neighborhood and delta p around p such that the image of that delta neighborhood through f is contained in the epsilon neighborhood you were given. Okay, so yeah, like the logic, has to be the order really matters. The order really matters. And like I said last time, for some functions, right, the delta doesn't depend. If your function is really sort of of bland behavior, then you can see that the delta. So if I take this point here and I say let epsilon be this length here. So here's this length. You see that I can use the same delta. I could use the same delta no matter what point I choose, right? Like here, p plus delta, p minus delta. This neighborhood gets mapped inside the epsilon neighborhood, right? If I choose another point p prime with the same epsilon, right? With the same epsilon, you see that the same delta is going to work, right? So here, like the delta doesn't matter, okay? But in general, the delta does matter, right? Right? The delta is going to change depending on your function. So let me give you an example of that. So delta depends on the point. So in general, delta does depend on the point. So consider the function f of x being 1 over x on, say, 0, infinity. So here, right, you have your function 1 over x like this, right? And suppose you take an epsilon of 1. Okay. You say I'd like to find a neighborhood where my function doesn't change by more than 1, right? Where my function doesn't change by more than 1. So suppose I look over here at the point x equals 1. Okay. Suppose I look at the point x equals 1. What kind of delta will work here? What kind of delta neighborhood here will ensure, right, the output, right, the f of 1 is 1, of course. How big of a delta, how small of a delta do I need to choose to ensure that my function doesn't vary by more than 1, Write down, take 10 seconds and write down what kind of delta would work for that. Okay, turn to neighbor and say, a delta of blah would do. I'll plug in my ears so I don't hear what you're saying.
We are running around one right, one right. So
On the right side,
if we
you go.
add a bit that equals to 1 plus.
Okay, I'm gonna unplug my ears.
one
Okay,
minus
so
exactly.
what kind of delta will do? Anybody? Anybody want to make a guess? What delta neighborhood, what radius around x equals 1 do we need to take to ensure that the out points don't change by more than 1 from, that the outputs stay between 0 and 2, basically? Anybody? Julia? No? Wong?
My thinking is to get like 1 plus n and then 1 minus n.
This is just 1. So what? Give me a number,
I think we haven't talked about number. I haven't talked about this.
Natalie.
Well, we said that on the left side, it would be 1/2.
Yes.
But on the right side, it could be anything, but then to have a symmetrical neighborhood, it doesn't have to be 1/2.
You want to take 1/2, right? Because we're taking a radius here,
Mhm.
right? If I took a radius of 1 even, that would be disastrous, right? Because no way does this thing vary by less than 1 in here, right? It goes up to infinity, right? So yeah, we don't. So yeah, so a delta of 1/2 will do, right? Right. If I take epsilon equals 1, then at x equals 1, a delta of 1. Any delta smaller than 1/2 will do. Right? Right. Actually, taking it, yeah, no, that's right. Yeah. Okay. Right? Okay. But suppose I were at 1/2. Suppose I were at 1/2. Then what kind of a delta would I want? To vary less than 1 at x equals 1/2, delta being 1/2 is definitely not going to work, right? Goes up to infinity within that radius, right? Well, what's the value at 1/2? 2, right? Right. The value is 2. Where does it reach 3? At 1/3, right? So just 1/2 minus 1/3, a delta less than 1/6 will do, right? Delta less than 1/2 minus 1/3 will do, right? But definitely 1/2 would not have worked, right? So sorry, less than or equal to will do. Is this making sense? Yeah, right? And suppose I'm at x equals 1 over n. Right, I think this is what you were getting at,
Yeah,
right?
yeah.
You were trying to figure out the general formula. Well, it's going to be 1 over n minus 1 over n plus 1 will do, right? In other words, 1 over n plus 1. Right, and so you see that depending on the point, the delta really matters. I'm sorry, depending on the point, the delta changes. Okay, right. As you get closer, to here, kind of obviously, right, the delta has to shrink. Has to shrink like on this scale. Like 1 over x squared, basically. Okay, so so this leads us to the idea of okay, but now observe. Suppose we consider say 1 infinity, not 0 infinity, but 1 infinity, right? Suppose we take let me take let's take 1 infinity. Okay. If we're on on this interval, so we're just on this this set here, okay? Then if I take my delta to be 1/2, if I take my delta to be 1/2 here, then that delta is going to work for everybody, right? Everybody here. If I take 1/2 infinity, then delta 1/6 will work for everything, right? In that case, the delta doesn't. You can choose a delta that works for your whole set, right? Here, in the initial case, on 0 infinity, we couldn't find a delta that worked everywhere, right? We had this epsilon of 1, and there's no way of finding a delta that works at every single point. But you notice that if we close it off, then we actually can do it. We actually can find a delta that works. Okay. So anyway, this leads to the idea of uniform continuity. Oh, why did I erase this? Remember, f continuous at a point in X meant that given any epsilon neighborhood, n given any epsilon neighborhood and epsilon f of x. Wait, let me make sure I get this right. Okay, given any epsilon neighborhood and epsilon f of x, there exists a delta neighborhood and delta of x such that f of and delta of x is contained in an epsilon f of x. Okay, so that's continuity at a point, right? And then continuous, on the thing means that you're continuous. Continuous on the set means you're continuous at every single point, right? So f continuous on x means you're continuous at each x in x. Now here's the important one. F uniformly continuous on x means that given any epsilon, there exists a delta such that if the distance between x and y is smaller than delta, then the distance between f of x and f of y is smaller than epsilon. Okay, so there's a delta given. I should escape this picture. Given some epsilon value.
Professor?
Yeah.
Is the function always monotone, or is the function be like
No.
squeeze?
No. Can be any function.
Okay.
Yeah. Okay. So given any distance here, let's say we have this picture of delta epsilon here. There's a delta, right? I can find a delta like this maybe. I can find a delta so that whenever I choose any 2 points within that distance here, their outputs will be within this distance here, right? So if I take any 2 points and they're closer than this distance, you see that their outputs are closer than this distance, right? So I take these 2 points, right? And you see that their output is closer than this distance, right? Okay. So this is what uniform continuity means, right? That, given any epsilon, there is this distance there's this distance, so that as long as 2 points are within this distance, their outputs will be within this distance. And you see that what that gives you is that, given any epsilon neighborhood, the same delta neighborhood, the same delta will work as the radius for every point down here. Okay, is that, guys kind of getting it? Right, so that's uniform, and you look like you have a question.
Yeah,
Yeah.
I was wondering if the reason that f of x equals 1 over x isn't uniformly continuous is because it 1 over n minus 1 over n plus 1 approaches, like, the bottom term approaches infinity, like it is approaching 0? Is that
Yeah,
one?
yeah, exactly, yeah. Yeah, so that's how you see that this thing is not uniformly continuous.
Okay.
Yeah. That it's basically sort of, you can think of it as sort of a constraint on the slope, basically.
Mm-hmm.
Right? If your slope is bounded, right? If your slope is bounded everywhere, then that will ensure uniform continuity. Right? Because that's basically saying that you have a maximum speed. Right? If you've got a maximum speed and somebody says, I want you to travel less than a mile, well, you can just say, I can figure out the time limit, how much time, you can say, okay, I'm only going to allow you to travel, 10 seconds. I know how fast so like suppose your car travels 60 miles, at most 60 miles an hour. And somebody says, I want to make sure that you're not going to travel more than 1 mile. Well, then you'd say, okay, restrict the person to travel, to drive less than 1 minute. Right? Right. So, if there's a bound on how fast your car is, in other words, if there's a bound on the slope, then you know that the thing is uniformly continuous.
Okay.
Right? Here there is no bound on the slope.
Mhm.
Right? And that's the problem here. Yeah. Okay. So this leads us to the probably the big result about continuity and compactness, even more so than the extreme value theorem. Okay, so it's this theorem that says that if you have a function on a metric space that's continuous, and x is compact, so f continuous guarantees that f is uniformly continuous. Okay, so continuity on a compact set forces uniform continuity. Okay. Okay. So yeah. So let's prove this. Okay. So here, here's the picture as usual. You have some compact set. You have some metric space. You have some function, right? And at this point, so we want to prove uniform continuity. In other words, given any epsilon, right? Given any distance over here, given any epsilon over here, there's a delta over here, so that if you're within delta, if you've got 2 points within delta of each other, their outputs will be within epsilon of each other. Okay, that's the goal, to say that given any epsilon can find the delta that works for that epsilon. Okay. Right. So given any epsilon, we want to find the delta that works for it. And we're going to use compactness, of course. So here's what we do. What we do is, so somebody gives you an epsilon. Somebody gives you an epsilon, and what you do is you cover y with epsilon over 2. Wait, sorry. That's not right, sorry. I got it wrong. Okay, right. So we have, sorry. So you're given an epsilon, and what you do is you say, well, look, for every single point here, my function is continuous, right? So I know that, I know that I can always find a delta neighborhood here that gets mapped into the epsilon neighborhood here, right? That's continuity. Okay. So what you do is you say, well, look, by continuity, every point in X has a neighborhood of some radius, which I'll call delta of P, because the delta changes. Right? We're trying to show that the delta doesn't change, but right now we're just all we know is continuity, so the delta might change. Changes depending on P, right? So every point in there has a neighborhood such that f of the neighborhood gets mapped inside the epsilon neighborhood of f of P. Okay, that we know for sure, right? And actually, what I'm going to do something that will seem a little bit odd, but you'll see why I do it later. I'm actually going to find the neighborhood that gets mapped inside the half epsilon radius over there. Okay, so because at the end, what I'm going to do is do some sort of triangle inequality thing. So, and I'm going to, because we want to do this for two arbitrary points, right? And so what we're going to do is take the distance. We're going to say, look, we're going to take 2 points and use a triangle inequality thing, and then have to add epsilon over 2 plus epsilon over 2 to get the epsilon. Anyway, you'll see why we do this.
It looks like a common technique.
It is a common thing. So it's almost a joke that somebody said, like, I realized that all of analysis boils down to like epsilon over 2 plus epsilon over 2 equals epsilon, right? Right. Like that's basically how a lot of analysis proofs end, right? Yeah, and that's how this one is going to end as well. Okay, so you say, okay, every point P has some delta neighborhood. There's some radius delta of P around P, so that this thing gets mapped inside the epsilon over 2 ball. Okay. So now, and now we're going to do something along the same lines. We cover X with these. This is wrong. Sorry. This should be a P. This was nonsense. I wrote delta. It was a neighborhood of delta, which makes no sense at all. It's a neighborhood of P. Cover X with these guys. Okay. So where P ranges over all of X. Okay. So for every single point, cover it with a neighborhood. Okay. And again, we're going to play a little. We're going to do something. We're going to take delta over 2 for similar reasons. Okay. Okay. So now, by compactness, kind of clear what we're going to do. X is compact. We'll take a finite subcover. By compactness, X is contained in some finite subcover. Right, there's a finite collection of points. Right, there's a finite collection of points whose neighborhoods cover all of X. Right, that's compactness, of course. Right. Okay. So now I claim that taking delta to be the minimum of these half radii will work. Okay, so you cover X with, the open cover. There's a finite subcover. Now take the smallest radius there. Okay, take the smallest radius among those from those covers, and that's what we're going to use as our delta. Okay, so now you say, well, look, why? Because if you have 2 points x and y in X, whose distance is less than delta, right? If their distance is less than delta, well, first off, before I say that, first off, you know that this point x lies in some in one of these neighborhoods, right? So delta p pi or 2 pi for some I, right? Lies in one of these things, right? Because it's the x is covered by these things, right? So x, little x must lie in one of these guys, right? So what does that say? That says that the distance, right? The distance between x and pi is smaller than is smaller than delta pi, of course. Right? So the distance between x and pi is smaller than delta pi over 2. Right? Okay. But you also know that the distance from x to y, the distance from x to y is smaller than delta, right? Distance from x to y is smaller than delta, which is smaller than delta pi over 2. Right? Because delta was the minimum of these guys. Right? Right? So that tells you that the distance of y to pi is smaller than delta pi. Right? By the triangle inequality, the distance from y to pi is smaller than the distance from y to x plus the distance from x to pi. Right? But the distance from y to x is smaller than delta pi over 2, and the distance from x to pi is smaller than delta pi over 2. Right? So this is smaller than delta pi. Okay. Okay. Right? So each of these things, each of these points, x and y, here's pi, is delta pi, right? And x and y lie inside there, right? Now remember how we chose delta pi. How do we choose delta pi? Delta pi was chosen so that the difference between any point and the value of f at this point and f at this point would be smaller than epsilon over 2, right? Okay, so we put those together, and the distance between this and this must be smaller than epsilon. That's the end, right? So then, the distance between f of x and f of y is smaller than the distance of f of x from f of pi plus the distance of f of pi to f of y, right? But each of these is smaller than epsilon over 2. And so we get it smaller than epsilon. Makes sense? Makes sense, right? So we're just using the triangle inequality sort of multiple, 2 times basically, right? So we start off, we say, let's let's choose deltas, let's choose delta neighborhoods that get mapped inside of epsilon over 2 neighborhoods, right? That's the first move. Let's choose delta neighborhoods that get mapped inside of epsilon over 2 neighborhoods, right? And then we say, okay, now cover the whole thing with delta over 2 neighborhoods, right? Cover the whole thing with delta over 2 neighborhoods, right? Take the finite subcover and then take the minimum. Take the minimum, right? And then you see that that minimum actually works to ensure that the outputs are within epsilon of each other. So that's uniform. So that's how you get uniform continuity. Okay. Any point of confusion? Okay, let's go on. So now we're going to talk. So that's the big result for continuous functions on compact sets, and this idea of uniform continuity is going to come in. Is going to be very important later on in the course. Okay, and if you go on and take complex analysis, this fall, then it's an idea that will show up there. In some sense, you don't have to know too much about uniform continuity itself. Rather, what we're going to use in the fall is that if you have functions that are uniformly continuous, then certain things will happen. Okay, so in some sense, you don't have to get this deep into the engine, right? You just have to be able to drive the car afterwards in the next course. But we're mathematicians. We want to know everything, how the whole thing works down to the bottom. Okay. Okay. So now let's go to something that I kind of think is of lesser importance, but it's also super important. So, continuity and connected sets. Okay. So let's recall a set E is connected if it cannot be separated, right? If it cannot be expressed as separated sets. As separated sets. In other words, as A union B, where A bar intersect B and A intersect B bar are both empty. Right? That was connectedness. Okay. And the theorem that we're going to give now, you can probably guess, F continuous on a connected set implies that the image is also connected. Okay. Okay. And the proof of this is pretty straightforward. We'll do it by contraposition. So by contraposition, we'll show that if f of E is disconnected, then E is also. Okay, so we'll show that not B implies not A. Okay, so suppose f of E is disconnected. In other words, there exists A and B. So, in other words, f of E can be written as A union B, where A bar intersect B is the same thing as A intersect B bar. And they're empty, and it's empty. Okay, and so we're going to try and get a separation of E, right? We're going to show that if there's a separation of the image, then there has to be a separation of the original set. Okay, so can you guess what we're going to do? You've got some connected set here. You've got the image f of E, and the image turns out to be separable. Okay, so this is the image. This is the image, and we're saying if you can separate the image, then you should be able to separate E. How are we going to separate E? How are we going to realize? Let me read it like this: like you're able to separate f of E into these two sets. Okay. We want to get a separation of E. What do you think we're going to do? Anybody have an idea? Anne?
Could we take the inverse image of both of them?
That's exactly what we're going to do. Right? We'll just take pre-images back here, right? We do have to say, so you say, well, look, consider G being the pre-image of A intersect E, right? And H being the pre-image of B intersect E. Right? We do have to say intersect E because we might get more, like when we take the pre-image, we might get more than E, right? Because some other things might get mapped into there, right? So we just want to get a separation of E, right? So let's just be careful. Okay. Okay. So So E is going to be is the union of G and H, and we want to show that G bar intersect H is empty, and H bar intersect G is empty. Okay, so you say, well, look, consider A bar. Okay. It's closed, right? So it's closed. So F inverse A bar is also closed. Right? The pre-image of a closed set is going to be a closed set because of continuity. Right? Right? Okay, so this thing is closed. Okay. Now, G bar is contained inside of F inverse A bar. Right? Let me make sure I get this right. Right. So G is contained. G equals this thing, which is contained inside of this thing. Right. And this is closed. So when I close this thing, it's still going to be inside here. Right. This thing is contained in here, and this is closed. So when I close it, it's still going to be inside. Right. Okay. So that tells me that F of G bar is contained inside of A bar. Okay. Okay. But F of H is contained inside of B. Right? F of H. So, but f of h is contained inside of B. And we know that A bar intersect B is empty, right? Since A bar intersect B is empty, well then, G bar intersect H must also be empty, right? Because, if they had a common point, that would mean that A bar and B would intersect each other. Okay, but A bar and B don't intersect each other, so these G bar and H must be empty. Must be disjoint. Okay, so that gives us this thing, and then the other way is exactly the same. Yeah. Sure.
Sorry, why is f of h a subset of B again?
Because H is F inverse B intersect E, right? So it's all the points in E that get mapped to B, right? So everything in H gets mapped into B, right? In other words, F of H is contained in B, right? That's just how we defined it, right? Right, here is A, here is B, right? Here's E back here, right? We split E into two parts, G and H. G is the parts that go into A, H is the parts that go into B, right? And so F of H is contained in B. Yeah. That's just how we created it. Yeah. Yeah. Okay. So does that make sense? Does that make sense? Basically, you see what we did, right? You start off with the separation of the image, and you pull it backwards. You pull it backwards. You get these two sets, and then you see that the closure of because of continuity, right? That's the key thing here. Because of continuity, the closure of G can't intersect intersect H. Let me quickly just say give the consequence of this. So, for example, then we have the intermediate value theorem. So if you have some function, on an interval into R1, and f is continuous, and say f of A is less than f of B, then any gamma lying between f of A and f of B must lie in the image of F. Right, you got this map, A, B, F of A, F of B, and here's gamma, right? Or if you like to draw it in graph form, here's A, here's B, here's F of A, F of B, and here's gamma. Okay, and so any gamma must lie in the image, and the reason is that why? Proof. AB is connected, and F is continuous. So by the theorem we just proved, the image is continuous, right? In R1. But we had way back when, not too long ago, we had a theorem that said, is connected in R1. We just had a theorem a couple weeks ago saying that if you're connected in R1, you're a linear continuum, right? Given any 2 points in the set, it contains any point in anything in between it, right? And that's what this is saying, right? So the image is a linear continuum by the earlier theorem. So of course, gamma does lie in the image. And that's the inverse, that is the intermediate value theorem. Okay, so, okay, that's it for today. See you all next time.